next is Laurent Mueller from DDCI, presenting Mission Safety Critical Software Environment.
There you go.
Okay.
All right. So who am I? My name's Laurent Mueller. It's a French name. Don't let that scare you. I'm not French. At least I don't speak it. I'm partially French. So a little bit about me. I'm been in the embedded industry for actually over 40 years. I have the gray hair to prove it. And I started off in engineering, hardware engineering way back when, had a lobotomy, went into sales. So I'm the VP of sales for DDCI. So that's a little bit about me. A little bit about DDCI. So we're a software house. We've been doing compilers, and we do operating systems for safety critical, mission critical. That is our thing. The company's been around for 35, almost 40 years. And our markets primarily have been commercial avionics. So you've flown on aircraft probably here that ran our software, either in flight controls, displays, engine controls, you name it. We're all over the aircraft. That's our pedigree, if you will. And our operating system, DOS, that I'll talk about today, was actually designed for that. It was designed for design assurance level A. It was designed for time and space partitioning, et cetera. So why am I here? Well, we're seeing a lot of traction for our product in space. And to be quite frank, the avionics industry has gone through a number of technical challenges, just like you have, space has, over the years. And, you know, they've tackled a number of the problems that I see here discussed this week. And I think it's applicable to perhaps take a look and see what's available in those marketplaces. And then before I dive any further, I'd like to step back here and take appreciation for the presentation that we had yesterday from ARFL and this morning from Northrop Grumman. In essence, many of the things that they were bringing up are things that are solved in avionics software, at least some avionics software, I won't say all of it. And that's part of what I'll be discussing today, how those objectives that were brought up can be resolved in this structure. So with that, sorry, I have two machines. There we go. All right, so I always like to start off with like a magic wand kind of thing. You know, dear me, did I do this right? Oh, there we go, magic wand. I'm a sales guy, so I always walk into customers, and I like to say, hey, if you had a magic wand, what would you wish for, right? And what I'm hearing here is obviously robust environment. You need a robust environment because obviously your equipment's up in space or being launched. Needs to run industry standard software. We've heard a lot about RTEMs, even 653 yesterday, and other things. Enables high assurance system to be updated, redeployed. Actually, Northrop Grumman did a good presentation about that. The need to reconfigure your system while it's out in space, right? And then, of course, ARFL talked quite a bit about security. So those are all needs that I saw, heard today. And if we dive a little bit further, what does robust software really mean? In my terminology, what we've experienced in avionics is basically the ability to contain a fault. You're going to have a single bit event, you're going to have a software failure, you're going to have something go on. And it'd be ideal if the software didn't allow the error to replicate through the system. Basically contain the fault so you can restart the application without taking down the operating system or without impacting the behavior of your other applications that are controlling your craft. Obviously, it's also good to have a proven pedigree. You know, you grab Linux off the shelf, well, you know, the latest version is going to have whatever pedigree it has. You want to have the ability to have integrity checks, make sure the software that you're loading, you're running, et cetera, are good. And then the other thing we've heard here, and you all know this, obviously, but the smaller your footprint, the less error prone you are, okay? So, and then the other wishes, as we mentioned, as we heard today, running industry standard software, and heard about that earlier. You know, bare metal or RTEMs, RMS, rate monotonic, something like that is also appropriate. And what's also interesting is the ability to run multiple applications or instances in any mix. So you may have ARINC 653 in some cases that were discussed yesterday, but maybe you need to have another you're bringing over RTEM's code or something like that. So an ideal case would be something where you could have multiple interfaces to the software environment. I'm getting there. Okay. And then another thing that we heard actually today and yesterday in the keynote speeches was the ability to update or add more features to your applications, but you don't want to change the behavior of your applications that are already running. So I'll call it out here, right? So unless you have a time and space partition environment, how are you going to do that? If you have Linux, you add a new application in there, everything's playing in the same sandbox, effectively. You might have memory partitioning, but you don't have other resource partitioning. So when you add a new application into a system like that, you can potentially change the behavior of other applications. So the analogy that was brought up by Josh from Northrop Grumman to add in a new application, right, or into a system, you don't want to impact the behavior of your other applications that are already certified and running. And then last but not least, there's a couple other things here. You want to be able to add new applications without doing a full reload, recompile of the whole bloody system. You know, you do that in space, it's going to take time, there's more risks, et cetera, et cetera. Another thing that came up yesterday with the ARFL's presentation was, I think the analogy was, I may have a space system that has Northrop Grumman software on it, Raytheon's, whoever's, and everyone wants to protect their IP, right? So you can't have source code commingling. Okay, then security. I think ARFL did a good job of presenting a lot of that. In essence, you need to have partitioning between your applications so that you don't have leakage of data between them. You want to have secure communication, secure boot, obviously. I don't know if this plays out well in this industry, but encryption at rest, we have some customers, particularly those that can have their systems acquired by competitors, whether they be commercial or governmental competitors, that can tear down your system. And so encryption at rest basically protects you from that sort of thing, or at least raises the bar of difficulty in getting that done. Excuse me, I'm a little bit nervous. Let's see, what else is that? Security. Yeah, I'll let it go there. All right, so with that, obviously, you know, I'm setting myself up, right? So we have an operating system called DOS. It's originally written by, or developed by Honeywell. It was designed for design assurance DO-178 level A, and it was the first operating system that was actually developed with time and space partition that was certified by both the FAA and EASA. And I'm talking about a time frame in 1998 is when it was first certified on Bombardier Global Express, today better known as the Canadian Regional Jet. So you've probably flown on that aircraft where DOS is flying with time and space partitioning. So that gives an idea of the pedigree. It's been around for 25 years. Excuse me one second. Okay. There we go. I already kind of said that first line, Adam. So first time in space partition going back to 1998, it's certified and flying in over 10,000 aircraft. So it dominates actually the commercial airspace today. And again, that's Good. Uh, So you may have a low design assurance thing. Let's say it's theoretically a box that's controlling the toilet on the aircraft, right? Who cares? Well, some people do. But it's not taking down the aircraft. So you can have those applications running at different design assurance levels all on the same processor. That's the way it was built. That's what time and space partitioning does for you. Well, that's that. It's also not dynamic. This operating system is not dynamic, which is important for security. You don't want to have the ability for an application to light up out of the blue. You don't want to have a terminal interface. You basically don't want to have anything in your software environment that is operating that you didn't want to operate. And that's the way this operating system is constructed. It's kind of like the inverse of Linux. Linux, you have a Wild West environment where you can do anything anywhere, right? And device drivers down in the kernel, same level as your operating system. That, in our view, is a bad idea for safety-critical, mission-critical systems. In our environments, the other way around. You have to enable applications to take resources to do anything, actually. And last but not least, it's the microkernel as well. Okay. As far as scheduling, there's three scheduling paradigms with this operating system. There's ARINC 653, which is a bit of a restrictive environment, to be quite frank, where you have a major time frame and you define what runs where in that time frame. And within each partition, they call it, you run a priority preemptive scheduler that has the ARINC, what they call the Apex APIs. And the beauty of this structure is you know what runs where all the time. Also, when we run RTEMs, it's really the same structure, if you will. These are windows of applications or partitions that can run within a major time frame. We allow you to run, let's say, multiple RTEMs applications all within a time frame. That way they're protected from each other. You don't have to do either one of those because neither one of those windows are running. We run rate monotonic, right? You're familiar with rate monotonic systems, perhaps. It was similar to what was given with the Berkeley paper yesterday, in that it's set up to have threads of execution running at various frequencies, harmonic frequencies, so you could have 2, 4, 8, et cetera, hertz, let's say, or milliseconds, threads running at that frequency, but you can't have 2, 7, and 13 threads that are running at that frequency, for example. However, difference between what rate monotonic in our instance and say what Berkeley presented yesterday is you can also have non-harmonic threads operating. Basically, we bound the amount of time that they can take. Also, because our rate monotonic does do time and space partitioning, when you define a thread, you define how long it runs, therefore it gives you your time partitioning, and then you can have threads of execution within a partition or a process like Linux. So it gives you both time and space partitioning. All right. This one. Other features in the operating system is built from the ground up. Again, flight controls requires redundancy. So it has features for synchronization between multiple machines, can do lockstepping. We have customers doing that today. It also incorporates what we call a data bus. It's similar to a DDS. It does data decoupling. So that way, in the case of, I forgot whose paper it was, I think it was Northrop, talked about changing the sensor and then changing their application because of that. In our world, if you use this data bus, you can basically shield your applications from changes because the interface allows you to add in an insertion function or a formatting function or something like that. So again, our product was built with the notion of reusing your binaries. Last but not least, it also supports multi-core processing, what we call BMP or bounded multiprocessing. It's just built again for design assurance level A. So you can have multi-core processing on an aircraft or on your system that still gives you a very deterministic behavior. That's what we're providing. And because of that, you can then build safety or mission critical secure systems. We do some tricks here. One that's rather unique is the operating system. It's a patented mechanism that we offer through software, we allow you to actually segregate your cache. So your L2 cache, that's where you get a lot of jitter in your operation. We allow you to segregate that per application, not just per core, but per application. And that slams down your jitter as far as your worst case analysis in multi-core systems. Let's see, high assurance updates. So the way DOS is built, normally, let me just do a contrast here. Normally you do all your development, you do compiling and then linking on your target, and you download a blob or maybe a couple files, right, that are pre-configured to your target. In our environment, we actually have a high design assurance level linker on the target. So it basically allows you to drop down files that then the linker on the target will take care of the symbols, load them, and execute. This is done extremely quickly. We have a customer, for example, that reconfigures, actually reboots their system and reconfigures their system in flight on flight control. So in other words, they're doing a 100 millisecond control loop, and they're able to restart their system, reconfigure it within 100 milliseconds. Try that with Linux. Let's see, what else is there? You get the idea, and I think some of the other features, and I'm running close to my edge of time. Security is a big deal, obviously. Because DOS is not dynamic, it doesn't have to have terminal interface, it allows partitioning of resources down to the cache level. It inherently, the mechanism that DOS provides on time and space partitioning is common criteria EL level 4. There's other things you can do to improve that. It also supports secure boot, secure communication, encryption capability today. So, getting on right on 5 minutes to spare, so that's good. So the bottom line is, here's an OS. It has proven pedigree to it. It has proven technologies that mesh with what I'm hearing from the speeches today or yesterday. Secure, robust. It has extensive tooling. Compiler, debugger, IDE, all that other good stuff. I heard about code coverage tools down at the object code level. Guess what we do? We provide a tool that does that as part of our environment. It has a very wide market usage, certainly wider than, if you will, you'd be augmenting resources and staff, if you will, people that are using DOS in the avionics space. You'd be able to cross-leverage that. We have a strong ecosystem. MathWorks asked me yesterday about a particular customer. We've already integrated with them. LDRA, Vector, your modeling tools, ANSYS, et cetera, all of that's already in play. We also provide a simulation environment. QEMU was mentioned on the previous environment. We provide QEMU as part of our development environment. That way you can do a functional development and testing of your binaries that actually run on your target. You can do that on your PC. It's not going to be real time, but you can do that. We also have other third parties that have simulators as well. So anyhow, you'd be able to cross-leverage that. There's been a lot of refinement in the product. It's got the biggest avionics supplier that it literally has billions of dollars worth of product on top of it. And Airbus, Boeing, others use it extensively in their aircraft, not maybe always directly. Last but not least, it's cost effective. The big expense with my product, or our product, is the certification package. If you don't need it, don't buy it. So you're down to development tools and runtime license. It's not expensive. So it's a way to do cost-effective development, achieving the objectives that I heard on the keynote speeches yesterday and today. With that, here I am. Oops. Any questions?
Okay, do we have any questions for Lauren?
Okay, so what is the primary argument to use DOS over embedded Linux with a real-time patch in modern aerospace?
Well, DOS will give you both DOS has a pedigree to it, a stronger pedigree, number one. Number two, it'll have more features to it as far as if you're trying to achieve a high design assurance system. Time and space partitioning is part of it, but then there's all kinds of other ancillary things around the environment for synchronization, et cetera, that's off the shelf and has a DAL-A pedigree to it, so you know it's robust. So you don't have to build it, you don't have to do anything to it, it's available as a commercial product. And I failed to mention, performance-wise, we smoke everybody. In our space, if you're dealing with a time and space partition OS, I'm serious. We love to have customers do benchmarks. We do contact switching in multi-core, sub 10 milliseconds. Definitely, it's more towards 5 between contact switch times, memory spaces, at that level, worst case. So our performance is really very, very strong. Something we really hang our hat on. As you think about it in a flight control system, you can't have a lot of jitter. It'd be bad. It'd be worse than turbulence. All right.
Okay, so a question about cost. How does the cost of DS compare to RTOS's like VxWorks or Integrity?
Let's see, to steal Bush's quote from long ago, where was it lighter and friendlier? Is a good way to put it. But we will be competitive. The development licenses are pretty economical. Their subscription the cost is dependent upon whether you're doing single core, multi-core, et cetera, and what libraries are added in. But actually, it's the same product. We just price it differently according to how your use is. But usually, a development license is going to cost you anywhere between under $10,000 to maybe under 20. That's it. And then there's a runtime license that typically it's a one-time buy. It's not that expensive either.
Does this run on RISC-V?
Not today. It runs on ARM, PowerPC, and x86. RISC-V is definitely roadmapped. We hope to have that maybe next year or so.
Okay, looks like we may be getting a question in. Why DS and not, why D lowercase EOS and not all uppercase?
That's a good question. Yeah, it's just like, why is DDCI DDCI? We actually dropped all the meaning behind it. We stick with the abbreviation. I don't remember why it was actually Honeywell that did that. It used to be known as Digital Engine Operating System. Yeah, we have some funny acronyms in our product.
Yeah.
All right.
Any other questions? All right. Thank you very much.
Thank you.